Hello everybody. In this lecture we will be talking about randomized data structures and algorithms. Throughout this course you have probably studied several algorithms, perhaps some of which were randomized. In today's lecture we will be specifically focusing on these type of randomized data structures and algorithms. In particular, we will be looking at skip list, which is a randomized dictionary, and we will be studying the overall structure and how the operations, the dictionary operations are performed in a skip list, and we will analyze the running time, the space complexity of skip list. Subsequently, we will talk about a very elegant algorithm for the min-cut problem. We will define the problem and we will present Kargar's min-cut algorithm, which is again going to be randomized, and then we will analyze the algorithm to show that it solves the problem in polynomial time. So, let us begin with skip list. And to understand skip lists, let us first recollect what a dictionary ADT is. It is an ADT that can store key value pairs, and you can search for key value pairs, and the key is what is used for searching. You can search, you can insert a new key value pair, you can delete an existing key value pair, and so on. And so you probably have seen dictionary ADTs in the context of binary search trees, and also possibly balanced binary search trees. And as you might recall, these data structures take up O of n space and O of log n time per operation. Now, today's dictionary data structure is going to be the skip list, and it achieves these same bounds on expectation. Since it is a randomized data structure, we cannot give deterministic bounds for everything. We will instead provide randomized bounds, and also interestingly, we will also provide bounds that hold with high probability. And what do we mean by that? The probability with which our bound holds is at least 1 minus 1 over n raised to the c for some fixed constant c. Before we proceed, you may wonder what is the need for a randomized data structure that provides the same bounds asymptotically, except that it is on expectation and or with high probability. So, a natural question would be, what is interesting about skip lists? And primarily, like many randomized algorithms and data structures, it is not so much an improvement in the running time, but rather an improvement in the elegance with which the data structure is constructed. It is quite intuitive and quite easy to implement as well. So, let us begin with some intuition for skip list, and let us start with a linked list. Now, unfortunately, a linked list will require omega of n time for searching. Why? Because as you well recall, if you want to search for an item, you will have to start at the head and linearly search through all the elements. And so, the analogy would be that it is kind of like a train that has to stop at every station, and to reach a station at the very end of the track, you will have to stop at every station, and it takes a long time. Now, so therefore, a natural question is, how do you speed up the search time in a linked list? Well, going with the analogy of trains, we can try to add an express lane or express track, if you will. And not all the stations are in this express lane. So, pick each station along the way with a probability of 1 over square root of n, promote that station to also be a station in the express lane, otherwise not. So, here is an illustration of a skip, a sort of an intermediate towards the skip list, which illustrates this analogy. So, now the lower level, the linked list level, corresponds to the slow lane, and then we augment the linked list with an extra lane, an express lane. And now, by the nature of the probability with which we have promoted some items to appear in the express lane, it is easy to see that the expected number of elements in the express lane is going to be on expectation square root of n. Why? Because there are n elements, and each of these elements is promoted with probability 1 over square root of n, and therefore, the expected number of elements in the express lane is going to be square root of n. Now, we do not count a couple of sentinel nodes that are always going to be present at the start and at the end of each lane. The number of elements in the slow lane between two express lanes is also going to be on expectation square root of n. Why is that? Well, if you let's say we 53 has been promoted. Now, we are interested in how many elements are there between this 53 and the next element that is promoted, which is 83. Okay. And it's the number of those elements is also going to be on expectation square root of n. Why is that? The probability with which each of these intermediate elements, say 59, 68 and 70 and so on, will be promoted to the express lane is 1 over square root of n. And so, this essentially measures the number of times we will have to toss this biased coin, of 1 over square root of n before we get a heads, and that is essentially following the geometric distribution, and therefore, the expected number of such coin tosses will be square root of n, and thus an expected square root of n after you see expected square root of n number of items in the slow lane, you expect to see one that has been promoted into the express lane. Now, this is great, because now what we can do is search for items. So, let us think of the simple operation of searching for an element. So, let us say we are going to search for 70. How do we do this? Well, we will always start at this particular sentinel over here. So, the leftmost sentinel and the topmost level, and from there we are looking for 70. So, we will try to progress along the express lane to the extent possible, and when we overshoot the element that we are looking for, we will retrace our path for just one step backwards, and then step down into the slow lane and search for the element in the slow lane. So, let us see how that works. So, now we are looking for 70. We go down the express lane, we encounter 37, we encounter 53, and then we encounter 83. Oops! So, we have crossed the 70 that we are looking for. So, instead we turn back and go down one level, and then progress in the slow lane looking for 70, and we find the element. So, now how much time would this take on expectation? And so, this you will have to verify will take order of square root of n time. It's not hard to see because the number of elements in the express lane is going to be square root of n on expectation, and then we already stated that between two elements that have been promoted to the express lane, the two consecutive elements, the number of elements in between in the slow lane is going to be square root of n on expectation. So, adding the two, you will get order of square root of n expected time to find an element. Well, let us see if we can extend this intuition a little bit. Obviously, if one express lane helps, what about more? Can we add one more, so get 3 levels or maybe 4, or should we add 100 levels? Should it be log n, square root of n? These are all very valid questions, and for good reason. The skip list has been designed to have on expectation log n levels, but this is not something that is enforced. Rather, it comes implicitly. In a skip list, instead of promoting each item to an upper level with probability 1 over square root of n, we instead promote each item to an upper level with probability 1/2. So, if you start from the linked list, the 0th level, about half of the items are going to be promoted to level 1. So, let us say this is level 0. About half of the items are going to be promoted to level 1, and then a quarter of the elements are going to be promoted to level 2, and so on. And this is of course the intuition with which we can say that the number of levels is going to be of the order of log n. We will formally prove this in just a little while. So, as you can see, in a in a skip list, we do not stop at the one express lane, but we go on to have several express lanes, and the number of express lanes is dependent on whether there is at least one data item in that level. So, if you look at this particular skip list, we started off with several items in the lowest level. About half of them got promoted to level 1 and a third to level 2 and so on. We do not worry about or keep track of the number of levels. We just ask, well, there is a 70, there is at least one data item in this level. So, that is a good level, but subsequently we will simply not construct it. But then if the number of items is a lot, you will find elements that do get promoted based on this very natural principle of being promoted with probability half. You will see a lot of some items getting promoted beyond level 3, in which case then you will add a level as needed. And when items get deleted, you may have to delete levels as well. So, this is a very elegant way in which you very naturally control the number of levels in the data structure. And searching is quite intuitive. Suppose we are looking for the element 68. Well, what do? We start again at the sentinel, the leftmost sentinel in the topmost level, and we search for 68. So, we go down here and we encounter 70, but 70 is more than 68. So, we come back and go down one level, and now we start searching. So, we go to 34. 34 is still less than 68. So, we proceed further. We again hit 70, which is again overshooting 68. So, we return, come down to 34 and search in this level, go to 37, need to search further. From 37 we need to go to 53, need to search further. So, we go to 70, oops, we have overshot our 68. So, we come back again to 53, go down one level, and we start searching 53, we go to 59, and then we find our 68. So, this is the manner in which we search for elements in a skip list. And of course, you can very easily imagine small variations of this this search mechanism, but this is one concrete way to perform search within a skip list. Well, how about the next operation that we might be interested in, deleting an element? Well, let's start with think about how to delete the element 83, for which we first need to search for that element. So, we perform our search until we arrive at 83. In fact, we might have arrived at 83 over here, but then from there we can come down. And all we have to do is look at 83. Well, it is we've spotted 83. We delete 83 from every level that it occurs in. So, the final outcome will have to look like this, and these deletions are very similar to linked list deletions. It is just that we need to remember that the item has to be deleted from every level. How do we insert an element? Now, for insertion, we will have to find the right location for the element to be inserted, and then we will have to insert it. So, let us see how insertion would take place. And again, we always start from the appropriate sentinel, and we are looking to insert 97. So, the first thing we need to do is find the correct location where we should do the insertion, and we follow the straightforward mechanism, and we find the location where 97 has to be inserted. And then now what do we do? We will have to toss an unbiased coin to figure out how many levels 97 has to occur in. And so, the first well, in this case, let us say we tossed a coin and we got 2 heads before a tail. Well, 97 always has to be included in the lowest level, and because we saw 2 heads before a tail, it also has to be included in level 1 and level 2, but not in level 3. So, this is how the operations work in linked list. In the next segment of our lecture, we will analyze linked list to see how it performs in terms of running time, in terms of space complexity, and so on.